ratio of the current desired harmonic and the adjacent harmonic. So as soon as the signal is clean, you have a very clear estimation of the phase. But when the noise is added, for example, in this scenario, you get bias and variance about the phase that makes it very difficult to be robust. And even more important is about the choice of the window. If your window has a very large side of level rejection, like a Blackman window, minus 58 decibels, you get a very good estimation error variance about the phase value in between. However, the length of the window is also important in terms of the frequency resolution. So it's all about the trade-off between how much frequency resolution and how much phase estimation error you can introduce. So we found these things in phase estimation concept and tried to use it in the speech enhancement. But before I move on, I would like to emphasize that why phase estimation for reconstruction is helpful. So what I'm doing is to replace some observed noisy phase with some enhanced estimated phase. But how it can be helpful, let's see. So first of all, when you think about reconstruction, we are talking about more than one frame at a time. We want to overlap and add these reconstructed frames. And the thing is, these frames are not independent. So based on what phase value you're going to use, you might introduce some distortion that might degrade the quality of the reconstructed signal. And by an example, I would like to represent what happens when you use a noisy phase or an enhanced phase. Here is a time domain signal representation of signal before and after synthesis. Here is the frequency representation. We are looking at the spectral amplitude of this selected frame. We are looking at the clean signal, noisy, and phase noise. So when you look at the clean signal, there is a very large ratio between the peak and to valley, which means that it is very emphasized that how it is articulated and this good perceived quality. But when you look at the noisy signal, it's not necessarily the same thing. But when you apply the synthesis window, and even when you modify the phase, you form you shape the waveform in a way that it's more similar to the clean signal, this red one and the blue one. So there is some noise reduction mechanism in between harmonics that try to remove these noise artifacts, and this is exactly why noise reduction is possible by phase modification. The most challenging part of this research within the last 5 years was phase estimation. And the reason why is when you look at the geometry of the problem, at each frequency being K and time frame index L, you have a speech signal component which is corrupted with some noise D. And then you get, as superposition of these two, or these two, you get the noisy observation. And due to the ambiguity in the sign of the sinusoidal phase difference, the cosine has no problem. It's actually an even function. So you have these both combination satisfied. But if you know exactly the sign of the sinusoidal phase difference, then you could select the one that was the optimal set. This is a very difficult ambiguity problem. And both of these two ambiguous candidates would satisfy all the observations. I mean, by observations, noisy magnitude and the noisy phase. And it took us almost 7 months to find out that actually it's possible to use group delay deviation, which follows the harmonic structure of the magnitude spectrum. So I'm showing you the group delay, which is the frequency derivative of the phase. And the deviation means that how much it departures from the linear phase of the window. And this could be used as an additional constraint to solve this ambiguous problem. So this was the origin of the whole thoughts and phase estimation and so on that I started with. The phase estimation by a geometric approach and additional constraints. But another challenge was this phase uniform choir. In literature of the speech signal processing, you can often see that phase is assumed to be uniformly distributed. And this is as a result of the independence of the real and imaginary part of the complex DOT coefficients. But once you assume this is true, then actually the noisy spectral phase is the optimal estimate, namely minimum mean squared error estimate of the clean phase, which is not what we want. So we don't want to rely on noisy phase, right? We want to do better than that. But let's have a look how these histograms are calculated. Actually, these histograms are calculated for very high signal-to-noise ratio components. So they are focused only on frames that we have very high signal-to-noise ratio. And once you think about more than one frame and think about the correlation of the spectrum in the time and frequency, you will get something like this, which is more structured and more correlated than this. And then that was exactly the reason why we departed from uniform phase choir to something non-uniform. And now I would like to explain you how the non-uniform phase choir could help us to move on with phase-aware signal processing. The idea is to replace the uniform phase choir with a non-uniform one, namely von Mises distribution. What is von Mises distribution? It's kind of a Gaussian distribution in circular domain. We are interested in modeling the uncertainty around the mean value of phase, which is kappa, and kappa is something similar to variance by Bessel ratio function. So when I talk about the phase variance, I'm also talking about concentration parameter, which is characterizing the von Mises distribution. The argue here was for clean signal, the phase variance of the first few harmonics is pretty low. So when you have very voice frame, this phase variance is stable and quite small. But when noise is added in observed noisy speech, you have a very large perturbation and this large variance. And we would like to reduce this variance to improve the phase estimate. And this was possible by the temporal smoothing filter. And that's what was the contribution with Joseph Fulmer. We had this idea. And here is the big picture of what happens. The idea was to first estimate fundamental frequency, namely we want to know which frequency we are talking about. So we assume a harmonic model about the speech. We assume that the speech happens at certain multiple of the fundamental frequency. And once we know the frequency, we could get rid of the linear phase part, which was the wrapping issue. And this was possible by the contribution from synthesis group of IRCAM in France. This speech synchronous harmonic model could enable to get rid of the linear phase, and then we had an unwrapped phase that we wanted to focus. And this unwrapped phase could be then used for temporal smoothing, and that's what exactly this idea was about, to reduce the variance in the unwrapped phase domain, and once you have an enhanced phase, you can use it for signal reconstruction. And the reason why phase enhancement could improve the noise reduction, I already explained it in previous slides. And this is one application of phase processing, but obviously I'm interested to show you even more advanced applications where we can use this estimated phase as new choir knowledge to improve the amplitude. Why not to use this choir knowledge to drive a new estimator? And then I will move on to robust mathematical speech recognition. The first example is obviously speech enhancement. So if you look to conventional methods of speech enhancement, we do have a spectral analyzer, a synthesizer, and a modification stage. The spectral analyzer is a short-time Fourier transform, as we explained before. The idea here is to calculate a gain function based on some signal-to-noise ratio estimates, which are driven by some noise estimation, and then this gain function is applied on the noisy signal to improve the amplitude. This is the conventional method that modifies only the magnitude, and then the modified magnitude together with observed phase is used for reconstruction, which is namely inverse Fourier. So there is no phase modification in this conventional method. But what I showed you so far was to modify the phase and use it for signal reconstruction. And now that we have phase information, why not driving a Bayesian estimator, namely minimum mean square error estimator, which is driven by technical expectation over the phase estimate. And we drive a phase-aware amplitude estimator. And now that we have a phase estimator and a phase-aware amplitude estimator, we can alternate between the two. This is the iterative idea that we patented and we published. And I would like to return back to the example that I started with. This was exactly the outcome of this iterative approach that converged in a few iterations could jointly improve the amplitude of phase.
She had your dog food in greasy wash water all year. She had your dog food in greasy wash water all year. She had your dog food in greasy wash water all year. She had your dog food in greasy wash water all year.
So With this iterative approach, it was possible to jointly enhance amplitude and phase. And apart from this first application, which was focused on speech enhancement, I would like to give you a second example, which is about robust automatic speech recognition. Unlike speech enhancement, here we are interested in what's being said, not how it is natural and how perceived quality is about. The speech recognition is about extracting some features from a time domain signal and then give it to a robot or to a machine that understands what was said. And this is a classification problem. We need to have some training step that we learn about these features, and they are trained and modeled, and then we compare them at the test stage to see what was being said. And the conventional methods that are used for feature extraction, namely mel frequency capsule coefficients, they work this way: that first the filter bank, which is non-uniform, to follow the human auditory perception, is applied to the spectral coefficients of speech, and then the energy is averaged within each channel of this mel frequency filter bank to calculate the coefficient, and we come up with 13 coefficients, namely mel frequency coefficients and derivative and acceleration. These features are used for training dictionary, and then are extracted at the test phase to be compared with the trained model to see, to classify what is being said. What we tried to answer in our research was to find out that how phase-aware signal processing could be helpful for robust automatic speech recognition. The idea was to answer two questions. First, if I replace the mel frequency capsule coefficients as the feature extraction, by fx I mean feature extraction, by fr I mean front end. So we might either process the waveform at the front end or extract the features at the back end. So the questions were, if I replace the mel frequency capsule coefficients as a conventional method with some phase-aware method, which is mainly modified locally, what impacts I can see in ASR. ASR is automatic speech recognition, how this might contribute to speech recognizer. The second question was how a phase enhancement is made. We discussed about phase estimation in the first place. Now we want to see how phase enhancement could help at the front end to the recognition results and the combination thereof. If I apply a phase enhancement together with a phase aware feature extraction, how these two can contribute both. And these were quite novel questions, which will be presented in San Francisco next month. This was a collaboration with Johannes Faringer, Tobias Strong, Johannes Stahl, and Frank. And here are the results of word accuracy rate, WAR, in percent. You can see that by each step of this phase awareness at front end or at the back end or combination, you can see some positive contribution, and the upper bound, which is given by clean phase, is already a very significant improvement, I would say. So if we had access to clean phase, which we don't, our estimator has still some errors, right? But if we had a better improved phase estimator, which is our aim anyway, we could achieve this significant difference compared to conventional methods that only rely on mel frequency capsule coefficients. So this was the two examples, and now concluding remarks. Before that, I would like to emphasize that the research that was conducted in the last 5 years was actually in a way cumulative, because by attending to different conferences and organizing European Signal Processing Conference in Hamburg, or the Audiology Signal Processing Workshop in Germany, and then editorial for a special issue which was focused on the same topic, presenting a special session in Singapore, and giving a tutorial session in Dresden. And currently with the book and the FF proposal, it was all contributive to find out about phase-aware signal processing more and more. And currently we have submitted a proposal for workshop in KTH next year about the same topic, and a special interest group in ISTA, which is aimed to do that. Conclusions. First, phase is a very controversial topic, and it can be helpful to push the limited performance of the conventional methods that rely only on magnitude information. And I would like to invite you to have a try on the toolbox that we have included in the book. And if you have any idea, please feel free to let me know. Second, we can do better than the noises base. Obviously, if we can replace it with something enhanced and improved, we can see immediately some noise reduction or phase aware speech recognition and so on. I only showed you 2 examples selected, but there are more examples about speech signal processing that we could discuss, and they are already in the book or in the review paper. But these are all about the speech signal processing. I would like to put some answers to the questions that I started 5 years ago, and the first question was, is phase unimportant? Well, it depends on signal to noise ratio. If you're working at the signal to noise ratio is very large, namely above 6 dB, you don't need to bother with phase estimator, otherwise you need something better than that. And the second question was, if it is possible, well, you might have a look to chapter 3, we have 6 different phase estimators discussed there, and even there is a comparison between all these estimators in terms of bias and variance and so on. Well, future works, it is still not finished. We have obviously only addressed a few topics, but there are obviously other directions that we didn't, and currently it's still ongoing at our group. For example, I only presented you single channel signal processing, but how about when we have multi-channel, how we can benefit from phase information and phase difference between them, like in beamforming. And about the reverberation, I know that Fraunhofer Institute is currently working on the reverberation and phase over signal processing, and it will be very interesting to see the phase of the multicast, that how we can apply these phase estimators and modify these values and see how we can reverberate and enhance the signal. What I presented was only on normal hearing people, but how about the hearing impaired people? If we apply these strategies for cochlear implant or hearing aid applications, maybe we could get some benefits, and this is under discussion already. And last but not least, some showcases. We presented some show and tell presentations in Lyon and in Singapore, but what is missing is something as a showcase on an Android or a Raspberry Pi to present to some companies or so on. And this is also ongoing. This concludes the first part of my presentation. I would like to now shortly discuss about the second part of my presentation, which is about the habilitation and how I will address the field of science in the speech signal processing with my habilitation shift. And I will support this with the publications, teaching projects, and so on. I would like to first start with the disciplines that you might find in transactions, article transactions of Urdu speech and language, and article international conference on speech and signal processing, both most prestigious journal and conference in our field. You will immediately find out these disciplines that are actually the blocks that I have been talking about in my fourth slide. So whatever that I have been discussing in this presentation or addressed in the book often are found in these disciplines, which you will find in this track of field of science. On the other hand, if you go to International Conference on Spoken Language Processing, interspeech, you will find the phonetic and symbolic processing, which is going a bit in a different direction. However, you can still find some overlap between the two conferences. So I would say that we are addressing this more than this one, and that's why exactly I chose speech signal processing as the application topic. And I would like to emphasize that what I presented here today was in the context of the speech signal processing, but what if we would like to extend it to two-dimensional signal like image? I've recently found some interesting ideas discussed with Thomas Koch from computer vision department. That's how about we try something like that, or even on biomedical signals like electroencephalograph and the structure of habilitation will be focused on the book that is accepted for publication in John Wiley and Sons. And all of the reviewer comments we try to formulate it to be accessible for undergraduate and graduate level students. And all the reviewers agreed that invitations to the community to consider exploiting phase is timely and potentially valuable. And the reason why we structured it in these 2 parts is to provide first the fundamentals and the theory and concepts about phase processing, which was not easy to understand and accessible. in the literature, and then try to present some phase estimation fundamentals, how to get it, and then providing several examples. I showed you only speech enhancement and speech recognition, while we could also discuss about source separation, that we want to separate the sources, like music sources, or two speakers talking at the same time, and estimating the quality. Last but not least, provided a toolbox which makes it even more visible, and that was quite interesting for the community already, and this will be accompanied with the book, and several future directions and conclusions in the last chapter. Then different publications, global papers, patents, and conference papers. It was a result of collaborations with master's students, PhD students, and international collaborations and research projects and all that. And the courses that I have been teaching since my master and in World University of Bochum and here in TU Graz, we're mostly focused on signal processing in general and speech signal processing in particular. And research fundings and projects. I'm currently leading this FBF Einzel project, which is focused on phasor and signal processing with 2 PhD candidates and 2 initial funding, and currently preparing the PRC stocking grant in November this year. And I was also involved in several more packages of the other research projects in our group, headed by Professor Kubin. And you can see, for example, collaborations with Vienna on dictation, speech dictation, and DIRHA project about distance-to-speech interaction, and currently discussing with cochlear implant group. And here are the master students and PhD candidates and postdocs that I had privilege to work with. I would like to acknowledge them. And this list of the students are here for reference. And this slide is about presenting the implementation of the research topic in other universities. For example, the 4 examples that I would like to mention here, although they are working in an institute whose name is not necessarily speech signal processing, but what they are doing as their research areas are very similar to the concepts and the blocks that I have been presenting throughout my presentation. And they are conducting research about speech signal processing and trying to address the signal enhancement, reverberation, echo cancellation, speech enhancement, robust speech recognition, and so on. Last but not least, I would like to acknowledge a couple of people. And first of all, I would like to acknowledge Professor Jan Kubin, who gave me this unique opportunity to conduct my research in the last 2 years. And many fruitful discussions and feedbacks that I received to make this happen. Professor Rainer Martin, my former supervisor in Germany, for my postdoc, who gave a lot of advices during writing the book. And Professor Bastian Klein, who visited our group last year, and I had the privilege to work with him for 2 weeks. Again, I would like to thank Jan Kubin because he made this possible and invited Bastian here to visit our group. Soren Holt Jensen, my supervisor at Auburn University, 2 colleagues of mine as a PhD, Professor Prankov and Professor Littersau, and my colleagues who believed in faith from the beginning and collaborated with different special session organization and special issue and so on, Jan Siciliano, Ryan Taibi, the young guns, some of them are here, Johannes Stab, Joseph Kurban, Gloria Maya, Anna Mali, Andreas Gaich, Mario Watanabe, Carlos Chacon, current master student, Martin Blas, Michael Krill, Johannes Faringer, Christian Stepko, Andrea Zabrowska, and my family, Master President and Thank you very much for